structural map identifies algorithm number 49, RSA, as a cornerstone of the cryptography and data tier. Before RSA, encryption relied on symmetric algorithms like AES. These are efficient, but they present a distribution bottleneck. The sender and the receiver must both possess the exact same secret key before any data is transmitted. This creates a paradox. If you want to securely communicate with a server halfway across the world, how can two strangers agree on a secret key over a network where every packet is being monitored? Secure digital commerce required a system where the lock used to hide the data is distinct from the key used to reveal it. In April 1977 at MIT, Ron Rivest, Adi Shamir, and Leonard Adleman formalized a mathematical solution to this key exchange problem. Following a Passover dinner, a sleepless Rivest stayed up working until daybreak. He drafted a scheme where the security of the lock was tied to the computational difficulty of factoring large prime numbers. However, the idea wasn't entirely new. A mathematician at Britain's GCHQ, Clifford Cox, had secretly invented an equivalent system in 1973, though his discovery remained classified for 24 years. This breakthrough shifted cryptography away from the physical risks of secret key handoffs and into the realm of one-way mathematical functions. Asymmetric encryption operates on a single rule. A message locked by a freely distributed public key can only be unlocked by a matching secret private key. A specific mathematical calculation links these two keys together, binding them as a pair. They function as a mathematical trapdoor. It is trivial for a computer to multiply two primes hundreds of digits long, but it is currently impossible to take that final product and reverse engineer the original primes. Global digital security rests on this single assumption that integer factorization is a one-way street. Generation involves picking secret primes, p and q, calculating a public modulus n, and deriving public and private exponents. To encrypt, raise the message to the power of the public key. To decrypt, the receiver performs the same operation using their private exponent. Using primes 61 and 53 gives a public key of 17, private key 2753. Encrypting 65 to the power of 17 modulo 3233 yields ciphertext 2790. Decrypting with 2753 recovers 65. Conversely, factoring a modern 2048-bit modulus takes longer than the universe's age. This security comes with a computational cost. Encryption is relatively fast at O of n spared, but decryption with a massive private exponent is significantly slower at O of n cubed. Even generating the keys requires significant processing power, as the system must search for and verify the primality of extremely large numbers. In the actual implementation, the core of the algorithm is a single modular exponentiation, executed in Python using the POW function. You can find the source code for these cryptographic strategies at github.com/cloudinum/50algorithms inside the Chapter 14 Cryptography Notebook. Because this math is so demanding, RSA is too slow to encrypt bulk data like video streams, leading to an architectural compromise. Today, RSA handles TLS handshakes for HTTPS, SSH key authentication, and secure email. We use a hybrid approach. RSA is used only at the start of a connection to safely deliver a small AES key. Once that secret is shared, the faster symmetric cipher, AES, handles the heavy lifting for the rest of the session. But this foundation has an expiration date. A quantum computer running Shor's algorithm could factor these integers in polynomial time, making current RSA keys obsolete. To learn more about the algorithms that define modern programming, you can find the full details in Imran Ahmad's book. RSA solved the key exchange problem using a one-way trapdoor. But there is another way to agree on a secret, one where the key is never sent across the wire at all. That is the story of Diffie-Hellman.